Okay, now the recording is on. Now we are going to go through the another example on the compression member. This time, please take a look. We now have the bracing for the y-axis as well. So that means you have to check both Lx and Ly for your design. Okay, now we have the PU equal to 250 tons. So when you see PU, that's the ultimate load. So that means this design is LRFD. I suppose I just want to give you examples on both design approach, but in this class, I think we are going to stick mainly to the ASD for your project and for the exam as well, okay? But now we know this is the ultimate load. And you know that you are going to have Lx equal to 750 centimeters on the x-axis. And this is the symbol of the bracing on the y. And the Ly, you have a quarter of 7.5 and 3/4 of that. So this one is going to govern, right? So we may have mentioned about this before in class that it is, of course, the most optimum idea to have the bracing in the middle, because if you face a case like this, you now know that this part is going to buckle first because it's longer. So why have the brace at that point, right? But in real life, you may not be able to choose where you can brace your structure due to some architectural demands or some obstacles or anything. So that happens. Anyway, that would leave us to the Ly equal to 562.5 centimeter. Okay, and I think we can use the same approach where we know PU cannot be greater than phi Pn, which is your design strength. And we are going to look for our nominal strength from our design tables. So I will move the phi to the other side, and Pn will have to be greater than Pu divided by reduction factor. We all know if it's LRFD, the reduction factor is less than 1. So this is going to increase the load. That makes sense. No, the load always increases either by multiplying by the factor of safety or dividing by the reduction factor, which is less than 1. Okay, and this is turning out to be 278 tons. Okay, now we have Lx and we have Ly, but we do not know which axis is gonna, go first. And we have this. So this time you are going to have to enter 2 design tables. Okay, the first one is Lx equal to 750. So we come here to the table with KL equal to 750 centimeters, okay? And this is for the x-axis, so you hit the table here. And one more thing, we are going to use SS400, correct? So we are hitting here. SM400 to SM, right? And KL equal to 750. Remember, this is for Lx. So we keep coming down until we see the load that exceeds 278. And voila, there we are. Okay, so from this table, you've got 281 here that is greater. So here is H300 by 300 by 106. Okay, that's for Lx. But for Ly, you're now going to have to hit the table with L equal to 562.5 centimeters. You can see that now the unbraced length is, weird, kind of weird. And you cannot expect that I will have table for every 0.5 centimeter, right? So rightly so, we do not have the table for this exact unbraced length. So what do? If this is your unbraced length and you don't have the exact number, I probably have every 50 centimeters. So I have 550 and then I have 600. So to use 550, that would be a little bit, adventurous, right? But if I use 600, it means I am being conservative because I use the unbraced link longer than what I actually have. And so when I enter this table for KL equal to 600, I will be on the safe side. Okay, because the approximate number that I will have from this should be higher than the one that we will calculate based on this number, because it's 562 is shorter than 600. You can use 550 and try to select the section slightly above your demand. That is also fine. Okay, so now we here 600, but this time is for KL over RY, right? So we use this column with SM 400. Okay, so that with this and with that, and our target is 278. So we keep scrolling down, 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 down. Okay, we got 286. So that would be our number. Okay, and that is H350 and 350 and 115. So now we got two sections. Which one should we use? Can you answer me, or you plan to stay quiet like that? Remember, when we consider KL over RX, which is KL is 750, it leads us to this. And it says for buckling in X-axis to be okay, in terms of the load carrying capacity, you need to use this section. But when you consider the buckling in Y direction, you are required to use this section. So which one do you use? Which one are you going to try? Hello? Well, you can see that if you are going to use the same section here, H300 by 300 by 106, it's probably around here, right? What's going on? And, you know, when you calculate the K over RY, that will lead to the nominal strength, it is less than what you need, which is 278. So we better start off by trying this section, okay? So we are going to try H350 by 350 by 115 kilogram per meter, okay? Now you got that, you can open your steel table, okay? 350 by 350 by 115, right? Mm-hmm. Let's change color. It's this one. See, that's 350 by 350. That's nominal size. We are going to use 115 here. You can also pick up your slenderness ratio of the flange and the web from this table as well with our calculation, or you can do it yourself. Keep in mind that the nominal size is not the actual size. Look at the depth of the section. It's 344, it's not 350. When you do the calculation, you must use this actual number, okay? The nominal size is just the nominal, it's not the actual, okay? And the width of the flange is also 348. Keep that in mind. And we have the area of 146. So we now go back, we know that A gross is 146 square centimeter. So we got the section, we need to perform the check, right? So step number 1 is local buckling. For the flange, It's BF over 2 and then divided by TF. This number, you can get it by doing the calculation yourself, or you can get it from the table here, which is 10.9. See, 10.9. So this is 10.9. Because we are using the SS400, so this one is going to be compared with the limiting value of 0.46 square root E over Fy, and you should be familiar by now that it is 16, so we are okay. The flange is compact. The next is the web. It's H over TW. Remember, it's not the depth, it's the edge distance between the fillets. And again, you can pick this up and it's 27.2. Some students would do this calculation by themselves and then mess it up, which is very, very sad. Okay. So now we are going to compare this with the limiting value of 1.49 square root E over Fy, which is 42.6. So we are okay. Now both the flanges and the web are compact. So we get the big okay, no local buckling problem. Okay, now we move on to step number 2. It's lateral buckling now. Am I going too quickly? Hope not. So we have to again check both axes. Okay, so it's going to be KL over R in X direction. And I didn't write anything about the support conditions here. So let's assume that it's a hinge like that. Okay. So K is equal to 1. And in the XL is 750. So this is 750. And I didn't write this. So let's write it here that Rx is equal to, let's go back to the table. That's your x-axis property. So Rx here is 15.1 and Ry is 8.78. Okay, so we can come back here and this is 15.1. This gives us, what's the number? 49.7. And for KL, let's move it. I'll run out of space. Okay. It's a good thing, right? In real life, you're going to have to erase everything. KL over RY is 562.5, right? The longest unbraced length in y-axis, divided by 8.78, and that is 64.1. So that one is larger. So you can say this one governs. Oops. And you are going to compare this one with the limiting value of 4.71 square root E over Fy, which is 135. And this one is greater than 64.1. So now you can say that you have the inelastic buckling, right? Okay, now I'm running out of space. Now we know that we are going to have inelastic buckling, but before anything else, we need to calculate the elastic buckling stress first, which is pi square E over KL over R square. Don't forget the square, you know, some do. And this will give you 4,900 kilogram per square centimeter. Remember, this is the elastic buckling stress, not the critical buckling stress. So it can be way beyond the Fy, right? Now, because we know the inelastic buckling behavior now, that's what's going to happen. So we are going to use this and plug it into our F critical equation. It is 0.658 with the power of Fy over this Fe, and then the whole thing multiplied by Fy. Okay, and this gives you 2020 kilogram per square centimeter. Now this is the critical buckling stress. And now you can say that your P nominal is this, right? Critical buckling stress multiplied by the area, which is 146, and divided by 1,000 to make this into tons unit. And it is 295 tons, which is greater than 278. So in the end, you can say use this H350 by 350 by 115 kilogram per meter SS400. Okay, so that's the end of your compression member. Is there any question? That's it. Compression member, piece of cake. Any question? Hello? Are you still with me? Hello? Anyone? So quiet. If you don't have any question, I think that's it for compression members.
Excuse me.
Okay.
Could you back to the table, please?
Which table? This?
No. Table in the example.
Okay. This is the excerpt from OA, which I already posted for you guys. So I just hit the KL equal to 600 table, and then this is KL equal to 750. Which one do you want to see?
Yeah, this one.
Okay.
As you can see, right, this is a pre-nominal, right? It has two column, but what difference that we're gonna use? Because this is SM400, right?
Yeah.
And it is still SM400 as well.
SM400 and SS400, in terms of strength, they are identical.
Okay. But why the value is not the same? With the same, for example, it's the same cross section, same size. Yeah.
What do you mean?
For example, the first row, 100 times 100. For
this
the
one?
section, yeah, this one.
This
will
one?
become, yeah. PN will become 12, right?
Yeah.
Yeah, but it's another one will be.
Also, you mean why are they the same like this?
No, I would like to know that why this column and the previous column before the n, why it will be n/a.
Oh, okay, this one. Good spot.
Yeah.
Good spot. You deserve a good answer to that. Now, I didn't mention this, but I mentioned that for compression member, the KL over R should not exceed 200, right? Have I mentioned that?
Okay.
So yeah, it's when you have a compression member, this is your limit. Whatever you have, you should not go beyond the KL over R value of 200. Remember, it's 300 for tension members, right? For the practical purpose, for transportation, for everything. But for compression member, anytime, anywhere, your KL over R should not exceed 200. And for this case, they become NA because the KL over RY exceed 200.
Okay, it's not.
So that's why you cannot use them.
Okay. Yeah.
Good spot. But one thing that nobody spot is why are these painted green? You see that? It's green, right? It's green. Why? And you notice that?
For the P
the
nominal
numbers are the same.
Yeah.
Because these green numbers are when the compression members are in the elastic region. And when you calculate the strength of the compression member in elastic region is only this, right? It's 0.877 multiplied by elastic buckling stress, correct? Fe, which is pi square E over KL over R square, right? That's your elastic formula, if you cannot remember. Can you remember that? It's quiet. Let me show you. Here. See, that's your formula when your compression member is in elastic region. So I can plug this in this right away, correct? So
Yes.
What does it mean? Oops, wrong one. See, do you see Fy in the equation? Where is Fy? Where is Fy? Oh, it's gone quiet again. No Fy, you see? No Fy. Which means when your compression member is in elastic region, the increase of strength doesn't help. So that's why when you are in the green zone, it doesn't matter which steel grade you use, you still get the same load carrying capacity. See that? You see that? So, you know, when because in elastic, we are nowhere near Fy, right? Our compression member is going to buckle very, very quickly. So it's elastic behavior. It all depends on E. It doesn't depend on Fy. That's why if you run into the green part in your design, then you know you are in the zone where if you have a problem, the increase of strength of material doesn't help at all. Okay? More questions, maybe? If there is another question, it's just like halfway through the first session. So I am going to start the next chapter if you don't have any question. So maybe give you a minute or two of a break to erase your random access memory to start on something new, okay? Let's take a breather for a minute. I still don't have it. Okay, we ready? Are we ready? So now it's on to chapter 4. We are going to get into the flexural member now. Okay, just 1 second. Good. Okay, so here we are. But before we start doing this, let me remind you again that what we've been doing so far is, you know, we are designing something, correct? And it's always, you know, we need to find the demand from the law and everything else. And then we need to make sure that our prediction is greater than the number from the demand. Insofar, we try to understand the behavior. Now we have tension members before. Now you know that under tension, your member is either going to yield or rupture. Okay, so that's the behavior of the steel under tension. But when you put it under compression, it's the problem with stability. It buckles and we need to approximate the critical buckling stress. And we have lateral buckling And then we also have local buckling, which may prevent your member from ever reaching the F critical. But now we move on to another affair, which you should be familiar with. Now we have this. So it's a flexure now. Now in tension or compression, the stress is always uniform, right? But the problem with the compression member is that you don't know what that stress is going to be, but you know it's going to be uniform. But for flexure, this the definition of the flexural member is that you have the load perpendicular to the principal axis of your structure. So the stress is now not uniform. So we are moving away from the first two, which is pretty simple. Okay. Now, this is not only that is not uniform, but now you have also a mix of tension and compression. And when we have compression members like this, and then you move on to the flexural member and you say you have compression. So if compression can cause this thing to buckle, what do you think about this one? You have compression in flexural members as well. So yes, buckling can occur. Okay. And we have emphasized on the fact that the F critical is a function of the unbraced length. Remember, it's not how long your member is. It is how long the unbraced length is. The length between the two brace points where you prevent the lateral movement of your compression member to occur. And likewise, for flexural member, the flexural strength of your member will also involve with the unbraced length. But because of the fact that not only that it involves the unbraced length, it also involves the stress that is not uniform. So we are going to start off by looking at the flexural member where first, oh, it's already in here. So first, the stress of this flexural member when unbraced length is, say, 0 or excuse me, or not an issue. Okay. Now, if we can prevent the stability problem under flexure, we may be able to reach the maximum capacity of our structure to withstand bending as well. Okay, so let's take a look. Okay, I always remind you that, you know, this is the wall between the load side and the resistance side. So here we are going to predict the flexural strength again. But before we do that, we need to understand the behavior of steel under flexure first. Okay. Now, let's say I can blast this. Okay. You can see that if you put some kind of a floor on the beam like this, this is the hollow core. This floor in turn will be able to help prevent this beam from moving. Okay. you have to try to find a way to make sure that your floor will not move, right? In any way possible. So when we do that, that kind of action will also help give us the full lateral support for the beam as well. So this beam, you can say the unbraced length or LB is pretty much like 0, where LB is the unbraced length. Okay, we can move on and see the next picture. This too, this is the metal deck, remember, where you need to attach it on the beam by the shear connector or the shear stud. So we're gonna have the shear stud in this direction, and in a way, this shear stud will help brace this beam. This beam is going to be braced by the metal deck as well. And you can say the unbraced length LB is pretty close to 0. Okay. And yeah, that's just like the drawing of that picture where you see here is your shear connector that connect the this metal deck to this beam. So this beam is braced. Okay, it cannot move at all due to the presence of these shear connectors. Right, but here's another issue. Now let's take a look at this beam. This is perhaps your primary beam, okay? Now, it doesn't have any floor sitting directly on top of it because the floor is going to be supported by, let me call this primary. Primary, where floor, where floor does not sit directly on top of it. Okay, and this is the, hang on. This is the secondary beam, right? The secondary one where you have the floor on top. So the secondary one where the floor is on top, you know, automatically we can say that the unbraced length is 0. But for the primary one, there's no floor to help brace. So that means the distance between this secondary beam becomes the unbraced length of your primary beam, because the secondary beam in turn will be the ones who help prevent this primary beam from moving. So that becomes the unbraced length. And if unbraced length is short enough, how we can say it's short enough, you know, in the future, you can say that this beam has full lateral support as well. Okay. So now when you have the floor or something like that directly on top of your beam, you can say that your beam is fully laterally supported. Or when your beam still has something to come in and brace, and then the unbraced length is short enough, how we can verify that, you see in the future, we can also say that our beam is has a full lateral support as well. Okay, so that's the basic behavior. We are going to get into that, and then in the next part we're going to get into when your beam doesn't have this, what do you do? Okay, but for now we are going to say we get into the situation where our beam can be considered having full lateral support And with that in mind, we can now study the flexural stress in your B. Okay. Now, this is it. Okay. This is your actual stress strain diagram for steel. You know, in reality, it's just gonna go up like this, do a little king, go flat, and then go up after strain hardening. But it's kind of difficult to use, right? So we are going to say we will simplify this by using this straight line instead. Okay, so that straight line will become our stress-strain relationship for steel in flexural member. And you know, this first part here, that's elastic, correct? I have to keep on doing this so that you can see better. That's elastic. And this one, it goes flat. It means that when you reach this, your Fy will not increase, but your strain keeps on increasing. So that is when you have the behavior called plastic. So you have the elastic here, and then you have the plastic there. So in turn, they call this simplified stress-strain relationship of the steel the elastic, perfectly plastic material. The perfect plastic means like go straight just like that. And we are going to use this for our design model. Okay, any question on this one? We're gonna come back here, but in order for you to grasp the idea, I should begin by drawing some pictures. Okay, so let's say if this is our beam, is it too big? Maybe anyway. And this is perhaps our stress-strain relationship. We are going to use this elastic and perfectly plastic. Okay, that's your Fy. That's your epsilon y, correct? That's a strain where the yielding occurs. Wow, slipped my mind anyway. So I have to find a proper picture. Done here, but I just want to know if I have to draw another line. No, not at all. Anyway, so let's say this is our neutral axis. When I load the beam, you can see in this. Okay, when the first yield occurs here, let's say this is strain. This is the stress. When the first yield occurs, I can say, if this is a strain in your section, this strain is equal to epsilon y, right? When the yielding first occurs. So it's right here. This is point 1, first yield. Let's first yield. And because it's where the yielding is. And now if you look at the stress, right here is when you have the Fy as well, right? That's Fy and that's Fy. So basically that's first yield, okay? But suppose I don't stop there. I keep adding the load to my beam, what's going to happen? My stress will not increase. My stress will stay flat, but my strain can keep going. Correct? So let's say here, when we are beyond the first yield, and now my stress is beyond the epsilon y. Say I use 3 blocks here so you can see that perhaps this is where your epsilon y is. But now your stress is greater than epsilon y. What's going to happen to your stress? What's going to happen to your stress? Remember that the stress will remain flat like this, right? So what happens is that now it could not go beyond the Fy, but right here, it will reach the Fy as well. So the yielding will creep in. So now your section begins to yield more than just the outermost fiber. When you have your mechanics of materials class, this is where we stop, right? Oh, okay, we reach the Fy, but for steel as a material, I think after the World War II, engineers discovered that actually steel can take more punishment. When it yields, it still can take some more load. So it's like this, you know, when you reach the yield point and then you continue to load, actually your steel beam is not considered to be a complete failure just yet, because you can still have the section yielding more and more and more and more, right? Until if I keep on doing this, and then my strain goes to infinity, right? It goes to infinity, just like this line goes, woo, like that. So this is going to be something like very close to a horizontal line, but you cannot have that in reality, right? So what's going to happen to your stress? So now you may be able to guess that, you know, the entire section is going to yield. So now we have Fy throughout the entire section. Okay, so this is a plastic. And when the entire section yields, at that particular location, it will form a hinge. So when you load your structure until another hinge is formed where the maximum moment occurs, that is when your structure is really going to go. Okay, and this is where we can reach in steel structure. So we are not going to use this typical first yield as our strength anymore. We are going to use the plastic capacity of our steel. Okay, so it's time to be introduced to the new stress distribution when plastic hinge occurs. That is our stress distribution. Okay, any question? Hello? Oh, my iPad goes down. Plastic hinge somewhere, maybe. Any question? Okay, if that's the case, we don't have any questions, so let's have a 10-minute break. All right. I may run a little bit late because I need to do something, but okay, let's stop the recording.